whenever we are interpreting breaks, we need to be very, very careful and also pay some certain attentions. You don't just interpolate or extrapolate when you have something in the middle, not actually joining them. You need to be very careful and try to bring in more subjective kind of data. Now, whenever you are doing that, just like what I've just said, you need to record whatever you are seeing, record them where you are seeing them. If you look at this map now, there is nothing within here and the bet. Naturally, some people will say they want to join it. That is the same thing. But if you look at here, there is a break here. So, yes, you need to understand what is actually happening here. Why is this data this way? Also, you need to actually record details. Try to record details. Many straight lines in geology actually assemblages of small segments and geometry of these segments show some critical information on the structural styles. So we need to understand that. You can see now, if you look at these two here, they are not of the same observation. Somebody here is observing east-west, someone here is more of observing north-south and kind of southwest. So also try to consider range of orientations while marking breaks, because some of these markings might be similar to flight lines, and this can actually form some artifacts while you are recording, and they may not be true kind of lines. So you need to be very careful and understand which line are you actually taking in terms of your flight lines. You need to understand whether your flight line is north-south or east-west. Because if you look at these two observations now, someone here, you can see this, you can see this, and you can look at this. So this looks like a kind of artifact that is formed by a flight. And if care is not taken, you can record this as a kind of fractures or a lineament, and you start following that. So we need to be careful about that. Also, we need to understand that less lines are actually more appropriate for first stage of interpretation. Some inclusion, you can actually do that later on when you have some more data to prove that yes, what you've done in the first stage is correct. So you need more integrations to come up with that. So we really need to be very careful and understand the flight line direction before you go on in interpretation. So now, when you are interpreting, this is very, very important, the white paper text, or what we call the white screen text. The white screen text, the white paper text. This is actually a procedure for progressively checking and validating your observations on paper or on screen, in isolation from imagery you are working with. So whenever you are working, you try to remove the image and look at the lines you are drawing, the observations you are making. Do they actually make sense to you? These observations, do you think that structurally this is actually what is happening? The observations you are making, are they fighting each other? So try to ask 3 questions, which is like, all these lines I'm drawing, are they reasonable record of what I'm seeing in the imagery? Secondly, you need to look, these lines, are they actually geological or not? Also ask yourself, in few years to come, or if I'm giving someone else this data to look at, will the person see these lines as structures? Will he see some sense in it? Do they have some relationship between geology or kind of, or do they have relation between the geology and the fracture, the structural styles within these zones? So that's actually what we are looking at. So you see, this is actually what we've done with the imagery, and this is when we remove the image, this is what we've seen. So this imagery, do they look geological? Are there some kind of intersection? Are there some kind of relationship within other kind of data you are having? So that it does it. Then let's see some of the work we've done. Let's do some kind of white paper test and look at it. Okay. Let's look at this image here. As we've explained this before, we were able to identify these rock units that are very broad, identify this rock unit here that are also very broad, and also identify this rock unit that are very broad, and we try to look at their contacts, because the contact zones are actually where we are interested if we are looking for hydrothermal depositions. So this is a broad going northwest and sorry, northeast. Here this is actually also going northeast, and this is actually different kind of directions. So when we've tried to identify some of these lines and these rock units, the boundaries, now this is actually what we are getting. This is what we've actually tried to do. The major ones, there are more details to this, but trying to, as I've said, let's identify the major ones first of all. Now, there is something here. If you look at this also, this is also another observation from different layer. But this observation is different from this. This actually is going north-south, north-south. But this and this actually marries with this. So let's try to remove this and see what we've done in white paper. This is what we call white screen. You can see without the image, this is what we've done. How does it look? Now, if we are to plot a Rose diagram of these structures and what we've identified, there's no doubt that most of the things here run in northeast. You see, we just see this also marries here, even though they are in different data. This is the different data and all that. That is it. Then let's look at this. This is all northeast, few north-south, and northwest, few of it. But most of the structures here are northeast. So looking at this, do they look geological? Is there any structural, what the structural trend is clear? The structural trend here is not riot, it's not kind of fighting, you can see it's not too noisy, but it's clear, it's clearly identified that this is the fabrics of the regional foliations within these zones. You can see it. And also, if we try to bring in some other kind of data to see, now let's use the first vertical derivatives in y direction. This is what we've seen. Then the gray, that is the color of it, looks this way. This is actually what we've seen here. Then let's look at in x direction. In x direction, we'll try to identify some in x direction also. Even the x direction gets some of these features. Then this is the first vertical derivatives. So this is actually what we have. So when we are talking about Y-screen test, it is observation. As you're observing, you are removing your image from your observation and trying to see if what you are doing actually makes sense or not. So you'll be able to, don't be afraid to go back, front and back, to actually delete what you've done and actually re-observe again. So never stop asking yourself these three basic questions. As we just said, you need to understand, yes, these lines are reasonable as I'm doing them, and these lines look geological, and even if I give these lines, this map to any other person, my colleagues or other professionals, they will be able to make some sense out of what I've done. And also understand that there is no single kind of the observation that is suitable for all types of aeromagnetic imagery. There are different observations based on geological settings, based on what you are looking for, based on the sense of what you are interpreting and the knowledge of the geology. Now, we also need to understand some specific issues that most of the time affect the integrity of observation layers. There are some issues that affect most of what we do. We need to understand that one is the geological control. Geological control it is very, very important that when you are making use of your geological data to interpret, it don't allow it to influence what you are interpreting. You need to understand that your geological data, in short, is there to guide you. But also have it at the back of your mind that your observations from aeromagnetic data should give you new insight, should give you a kind of new insight in geology, new insight in what you are actually trying to also interpret. Most of the time, some people, there are some school of thought that will say they will interpret to that geological map. They just interpret, and most of the thing they are interpreting becomes mechanical. But I don't buy into that. I think that for you to make some interpretation, what you need to do is to be objective as much as possible. The objectivity counts here. Trying to bend whatever you're observing to fit in some theoretical perspective or existing or pre-existing kind of mapping or model is not actually the best. Though most of the time it's very, very tempting for you to say, yes, this is the geology of this area, it looks that way. But why am I seeing this kind of features, in my aeromagnetic data? So some of these preconceived things is valuable, but we must avoid letting some of these observations, being beclouded by what has been existing on the ground. Also, we should understand that depth variation is one of the key issues here. Most of the aeromagnetic survey would show features sourced from a range of depths. We need to differentiate the shallower magnetic source from deeper magnetic sources. In our subsequent kind of work, we might try to go deep to see how we can filter out shallow sources, deeper sources, and all that. But right now, we are trying to look at observing aeromagnetic data, the patterns, the trends to follow, the break, the discontinuities, the magnetic rock unit, and some of the specific issues and the way to go about that. So if you look at this is a kind of a granitoid texture and a broad magnetic zone. Geological control. If you look at this, here is a one vertical derivatives of RTP. We try to merge with other kind of data. This is a thorium count, and we are able to show this. I will show you the geological map of this location. So we should be able to understand that yes, we will make some inferences. We try to, from the map, we try to look at what is the geology also saying. Is it actually saying the same thing? So that is it. Then depth variation also, as we just said, is very, very important in trying to interpret. If you look at this now, you can see the increasing depth to magnetic rock. Now you ask yourself, it doesn't mean that when it comes here that this is flattening up because this is actually the shape of the rock. No, it's because here the rock is deepening. Because the rock is deepening, the resolution is lost. You can see, but here the resolution is clearer here. So that's why when the anomaly shapes widens, our definition becomes poorer, the contours will start fading away. So that's actually what we've seen here in delineating the deepening magnetic kind of rock in this example. Another thing we need to look at is some of anomalies definitions. How do we define our anomalies? Most of the time we'll say magnetic anomaly, geological anomaly. What is actually anomaly? In a very broad sense of it, magnetic anomaly in a continental scale map is just the difference between the measured field and the IGRF. So this is actually what we need to understand here is that one, when we are talking about anomalies, we can say yes, specific magnetic highs and lows. We can look at them and say that yeah, there's an anomaly here. On our images or on our profile, there is no straight way of defining anomalies. Anomalies can be, can be subjective. It can depends on what you are interested in. You know, the lows and highs cannot actually form an anomaly. Also, even the features, when you see features that are not usual, that are actually truly unusual, you know, you are not expecting them in this kind of geology. In the context of what you are working at, you find out that this feature I am seeing here is not supposed to be here. So why is it here? That is an anomaly. It's like, you know, the different from the normal. You know, when the it's not the norm, you say this is an anomaly. So that is it. Another one is when you can look at some extreme low field intensity and high intensities. You know, minus 2000 nanotesla is not the same thing as plus 2000 nanotesla. If you are seeing minus 2000 and you are getting plus 5000, they are not the same thing. These are a very, very wide range, you know, in terms of magnetic intensity. Another one is, we can say, some of the unusual changes in the geometry of magnetic rock. Yes, we can call them anomaly. So they can also form anomaly. You know, so there is no clear formula for defining anomalies in magnetic map or even in geology. So anomalies are actually where you found them and what you define or what you are looking for. That could be an anomaly. Anomaly, what you think that is an anomaly in another geological environment, like maybe possibly in a banded iron formation, might not be an anomaly in another formation. So that is just it. So there's no clear formula to say when you get this is an anomaly, or when your intensity is up to this is an anomaly. No. If the background value, for example, is 5000 and everything rounds within 5000, assuming you are between 5000, 6000, and suddenly you are seeing 15,000 in one location and all that. That is the intensity is so broad, the difference is so high. So that could form an anomaly. You know, so if you look at some of the examples we have here, we can look at this. This is a magnetite banded iron formation from Takula region, South Africa. You can see the intensity. Yes, you can see the intensity is greater than 5000 nanotesla, and the area measures 40 kilometers by 40 kilometers, courtesy of Christian Anderson. So this is a clear anomaly in this region. You know, it's a clear anomaly in this region. Also, you look at this image you have here, the alteration zones of annihilation. The intensity is minus 2000 nanotesla, you know, gotten from Fugro Airborne Survey. So you can see that this is also a very clear anomaly. Why? This is an alteration zone, you see. So this is then look at another image here. We have some pyrrhotite rich maker zones, you know, ranging of about 900 nanotesla. Low densities goes down to minus 450. This image is about 3 by 3 kilometers. So this is actually gotten from Northern Territory Geological Survey. So it's a clear anomaly within this zone. And also this image D, you can see another clear kind of magnetized ultramassive seal is an anomaly. The intensity of minus 4500. You know, so that is a clear anomaly. So anomalies can actually be found in some places, you know, that when you're not supposed to see them. So you begin to ask questions about, wow, this is not supposed to be here. So we look at the scale of observations. Whenever we're observing, there are two major kind of scale we can use. Is either we're observing in quasar scale, which is very big scale, or we are actually observing in a final scale. One is that, you know, if we are working on a very regional data, it allows easier recognition when you are using a quasar scale. You know, it allows easier recognition of broader variations and serves as an overview. So the records at these scales are generalized, but much details are not actually found, but it allows you to see generalized feature on a regional trend. So if you look at this is observation in 1:1 million. Meanwhile, this is an observation in 1:250,000. Now, if you look at these two, they are not the same thing. Here you can observe the features here in 3 You can see in three distinctive features. You can mark this one, you can mark this two, and this whole place looks as another kind of features. But here is more detailed, but it's not broad. So this is the final kind of scale. This readily facilitates the extraction of the desired level of detail in data. So it can require time, care, and attention for you to specify, to be specific during observation. So let's look at zooming in and out. When you are digitizing or you're observing your features, you need to understand that there are some people, when they are observing, they are bringing out details. If you are mapping in 1:10,000, you must zoom in, you must understand all your zooming in must be 1:10,000. Okay, let's see this now. Okay, we are here. You see, at this scale, this is 1:1.5. We zoom in, this is 1:1 million. Now, it is not more detailed, no more detailed. We might not see all the features and more detailed and all that. So, if you want to observe certain things, you want to map in a very, very, very low scale, you need to understand what you are doing. So, and again, your zooming in depends on the resolution of your image. We can see more detailed features here. You see, we want to do in more work. Now, some of these finer details, smaller details, we didn't bring it out. At this scale, they are coming up. This is 1:100,000. At 1:100,000, we are observing this image now on 1:100,000. So everything will show up. Everything will show up. If you see, a lot of things we've not identified here. If we are going in, zoom in, the more we zoom in, you see, the more the features appears. You can see this is 1:20,000. You can clearly see a boundary here, and you can clearly see boundaries here. You can see it. You can see this and that at this scale. You can see it at this scale. You can see boundaries. You can see boundaries, for example, and you can see strong boundaries here at this scale. Then if I'm going in, going out on 1:100,000, those boundaries disappear. So you must understand the scale of your observation. What kind of details are you looking for? Are you mapping, if you are doing something, an area that is just 5 kilometers by 5 kilometers, and someone is working on an area that is 50 kilometers by 50 kilometers, they are not the same scale. They are not going to have the same details or the same observation. So if you try to do that, you have a very clustered kind of work. So that is actually what we mean by observing in different scales. So you need to understand this. Thank you for actually listening. Ensure that you subscribe to our YouTube channel for future notifications, so that from time to time you will get some of our free videos, and there are some of our trainings that will give based on registration, and some will actually give based on request, and all that. You can also have access to that.